Hi, welcome back. This is Arun again, and in this video, I'm going to focus on one of the most important CCA 175 exam topics. This is to read and write files in variety of file formats and by using compression codecs or techniques. Hadoop ecosystem supports several file formats, and the exam is assessing your capability in accessing, transforming, and storing these files. You can accomplish majority of the file manipulation tasks using simple API calls via Spark or by using some command line arguments using scoop or maybe via using Hive by creating a Hive table that points to a file which is compressed in nature. I recommend that you master the data file conversion techniques and understand the limitations. You should have an alternate method of accomplishing a solution to a problem in case your primary method fails due to environmental problems within your Cloudera environment. Now let's get started solving this problem. This problem is asking you to download the data that is available in the orders table in MySQL into a particular folder in HDFS. And the file should be a text file and it should be tab delimited and the new lines should be separated by a new line character, which is a default character in scoop anyway. So let's start writing the scoop command. I'm going to do scoop import connect and as usual it's JDBC MySQL quickstart.cloudera on port number 3306 and then connect to a database of your choice, and by default retail underscore db is available on Cloudera environment, so I'm going to use that. So I'm going to use a password which is the default password for this Cloudera environment, MySQL database. The username is retail underscore dba. The table I'm downloading is the orders table as a text file, and then I'm going to say fields are terminated by the tab character. I'm not going to use the lines terminated by because by default the lines are terminated by the new line character. So there's no point of mentioning that and wasting our time. And the target directory is the directory that I copied from the problem statement itself. Okay, this failed. Let's investigate why this failed. There are two reasons why this failed. I think the first reason is the fields terminated by is is supposed to have a hyphen. I think that is the only reason. So let's wait until this finishes. This finished execution. Let me open another window. Oh, sorry. This is retail underscore DBA. Fine. So I think we have added another A in it accidentally. So let's try to correct this by correcting the name of the database. So all I'm going to do is remove the A from retail underscore DB because the right database name is retail underscore DB. Okay, this finished execution. Now let me open another terminal so that we can query the HDFS and understand all the files that are created. And I want this to be a clean view. So that is why I'm opening another terminal, and so that we can compare different file formats and the amount of space they contain. Okay, now this is split into 5 files. This is not, I prefer just using one file when we are comparing multiple file formats. But in general, you need to let the partitions be decided by Hadoop depending on the number of nodes available. So for that purpose, I'm deleting this folder again. I'm going to run this execution of scoop again with m as 1, which is number of mappings, which is one mapping. So now let me try to inquire HDFS again by doing a Hadoop fs-ls h is human readable format, and slash text. Okay, so now as you can see, one text file is created, which is a desired way because we are just comparing, but not in real time, guys. In production, you would want number of mappings to be in tune with the number of nodes that you have and in tune with your organization's preference. Okay, so next step is to download an Avro file, the same table, the orders table. So all I'm going to do is as Avro data file and then click enter. Okay, this failed. And I think this is because there's no space between the Avro data file and target there. So let me put a space here, enter. This should work. This finished execution. Let me do Hadoop fs-ls again and inquire about this file. Okay, as you can see, the Avro file is 1.7 meg, whereas the text file is 2.9 meg, which clearly indicates that Avro has a better compression technique internally. We haven't used any special compression formats yet. We're just using downloading files as plain Parquet file again this time. And earlier we downloaded them as the text file and an Avro file. When this finishes, okay, this finished execution, and I'm gonna inquire HDFS again and try to see if the Parquet file has been created. If it is, then we'll compare the size of orders data when downloaded as text, Avro, and Parquet. As you can see, the text file is 2.9 meg, the Avro file is 1.7 meg, and the Parquet file is 476 KB. No wonder Parquet has provided the best compression within the file. So that is why Parquet has been used widely across several enterprises. Now let's go back to the problem and see what is our next step. We finished step number 1, 2, and 3. The third step is to take data in the Avro file that we just created, which is orders data, and transform that into multiple different formats. For this, I'm going to use Spark Shell. Now, because I'm using an Avro file and the Spark 1.6 does not have default support, I have to uh, import special packages. That is com.databricks.spark.avro underscore. Now, this will ensure that the Spark shell that you're working in now has ability to read Avro files via the SQL context. So let me load the SQL context dot read dot avro in the name of the file. Okay, so let me hit enter over here. Now we have, okay, let's wait. This is going to take a little more time than normal because this is the first time we're trying to load an Avro file, but subsequent loads are going to be faster. So we have to, the problem is asking you to translate this or convert this Avro data file into a Parquet file using snappy compression. Now, in order to do the perform the compression, all you need to do is to set a configuration parameter called spark.sql.parquet.compression.codec. Now, you need to remember these terms because in the exam, you may be able to find them by looking at the API, but it's going to be time consuming. Remembering these and learning these by heart may save a ton of time for you during the exam. So now that I have set the default compression for the Parquet files as snappy, let me just write this Parquet file. I'm trying to repartition this into one partition so that I can get only one file, which will be easier for us to compare. Once again, I'm repeating this. This is not an ideal way of doing things in production, but during the certification exam, you can do it this way because it will be easier for you to manage one file instead of managing multiple files if you have to do any debugging. So now let's wait for this to finish. Okay, this has finished. Now let's try to inquire Hadoop or the HDFS and find out if the file has been stored in the way that we requested. So I'm going to say copy and paste it and then wait for HDFS to respond to my request. Okay, as you can see, the compressed file is 270K, whereas the non-compressed Parquet file was 476K, which is 100% efficiency when we did the compression. Now let's look at the next part of the problem. This is to do a gzip compression of a text file. So we need to convert our Avro data into text format first and then store that text formatted data in the gzip compression into HDFS again. For this, I need to extract elements from my Avro data frame into an RDD. So all I'm going to do is access the elements using index starting from 0 to 3 because the order table has 4 columns in it. Now I'm going to do a tab separation just so that it is consistent with the text file that we downloaded earlier using scoop. Plus x of 2 plus character again plus x of 3. Okay, let's try to print the result just to make sure that we have the result in the desired format. I'm going to take the top 5 elements and do a for each and println, which is a common method to inquire about the data that you just created. Yes, it is. in fact tab separated. Now all I'm going to do is use the save as text method. This is different from what we have done with the data frames. So you need to remember how to manipulate data and the variations that we have to do in order to save data in different formats and deal with data in different formats. Now in order to compress this data, I need to provide a codec, and all I have to do is to provide a class of the codec, and Spark will take care of engaging that class in creating a compressed format file. So all I'm doing is org.apache.hadoop.io.compress gzip codec. Now this has finished execution. Let's try to inquire HDFS again, and the folder name here is text-gzip-compress. Okay, so the compressed gzip file looks very encouraging. We have 453.4 kilobytes, whereas earlier when we downloaded this data, the data was 2.9 megabytes. So compression can do wonders. However, choose your compression technique very carefully based on the need. Do not use a golden hammer rule and compress everything into your HDFS and get into trouble at a later point. Okay, for the exam, this should be more than sufficient. Now, without doing any compression, transform the Avro data into sequence file. Now, sequence file is a key value file, and both key and value should be serializable in nature. And by default, the text data in Spark is serializable in nature. So all I'm going to do is create a key value pair. I'm going to say x of 0 as key, and then the entire tab separated x as the string as a value. So let me just do this again. So I'm going to say save as, I'm going to first change the path and then change the method name from save as text file to save as sequence file, and then map the data in such a way that it is a key value pair where key and value are serializable in nature. And as I said earlier, um, x of 0 and the remaining string should be serializable. However, if you can see, the x of 0 is any right now, so you need to convert that into a string, because when you fetch something from the data frame is giving you any object, not the string object by default. Okay, now this is saved in the sequence file. Now let's look at the sequence file by inquiring Hadoop. So I'm going to change the path to the path where we stored this file. It's a sequence file. So, okay, as you can see, the sequence file is 3.3 megabytes, which is way more than the the text file that we downloaded earlier. This is because it has a key value pair and it is a different format altogether. This is definitely not may not be efficient in certain scenarios, but I once again choose the file format based on the scenario very carefully. The third one, the last step in step number 4 is to take the same Avro data, convert that into text, but this time store it with snappy compression. So in order to store it with snappy compression, we need to perform the same exact steps. However, supply a different codec. Earlier, we supplied a gzip codec. This time, we're going to supply a snappy codec. So I'm going to reuse the statement that we executed earlier, which is save as text file with a path and a codec, and then I'm going to change the path to text hyphen snappy. Let's see what happens. Now, see, this is what I was talking about. This failed. Now, to fix this, there are ways, but during the exam, you cannot get into those ways because they'll be very time consuming. This failed because the build of Hadoop that is there with Cloudera right now does not support snappy compression. So how do you save this file in Snappy and score the marks that you need? Now, during the exam, you need to remember one thing. It does not matter how you accomplish the solution, but the final end result is most important in many cases. Now, in this case, if you can see, let me close these windows. Uh, the problem is not asking you to do any transformations. All it is asking you is to get the text, get the orders data in a text file using snappy compression. Now, why do we even need Scala for this? All you need to do is download the same orders data using Scoop and using snappy compression as a text file. Isn't that much easier solution? So you need to have a presence of mind during the exam so that you don't waste time in trying to solve problems in the longest possible way. You need to solve them intelligently in the shortest possible way. And in this case, the shortest possible way to do this is by using Scoop without engaging Spark at all. So all I'm going to do is enable compression, and I'm going to give compression codec as the same codec that I've used in Spark. It did not work in that case, but it will work here because the Scoop is an external library, and it has its own method of compressing. It does not have too much dependencies on Hadoop, and only after the compression it stores the file into HDFS. This is how you solve the problem. There are other ways of solving this too. Let's say your problem is asking you to do some transformations, then Scoop is obviously not a solution. In that case, uh, you need to use Hive in order to accomplish this. All you need to do is create a Hive table and point that table to this new file, and enable compression in Hive and do an insert into this table so that you have data in the file format that you need. You need to make this decision very quickly during the exam. The next step is to read a compressed data file. If you compare this with step number 4, in step number 4, you read a data file that was not compressed. The Avro file which you read in step number 4 is not a compressed data file, whereas in step number 5 it is a compressed data file. There is no difference in reading a compressed or a non-compressed data file in Spark. You will be using the same exact method for loading a compressed or a non-compressed data file. In this case, because it is an Avro data file, sorry, a Parquet data file, I'm going to use .parquet and you know copy the Parquet data files path to this place, and I'm going to load this in a variable so that we can use this for further processing. Okay, next step, as you can see, the Parquet data file has loaded. Even though it is compressed, there is no difference in which you load the data file. The next step is to transform this into a non-compressed data file. Again, a Parquet data file which is non-compressed. So now we are translating a compressed file into a non-compressed file, which is exactly opposite to what we have done in the past, where we took a non-compressed file and put that into a compressed file. For this, we need to set the codec in the same way. Earlier, we used a snappy codec for Parquet. This time, you'll have to say uncompressed, which means do not use any compression mechanism. You need to perform this step to help Spark understand what to do when dealing with Parquet files as an output. Now, all you need to do is .write Parquet and give this path. Now, this has thrown some exception. You can safely ignore it because this has nothing to do with the problem that we are trying to solve. All we are trying to do over here is convert from one file format to another file format. So let's try to inquire HDFS about this particular file. Hit enter. Now let's see what comes up. Okay, as you can see, it's 477.3K. Now this is a very similar size to the Parquet file that we had earlier. Now, the Parquet file that we had earlier was around 478K or something. Now it is 477K, so it should not be a big difference at all. The next thing is now taking that and converting this into an Avro file using snappy compression. Okay, so I'm translating a Parquet file in a particular compressed format into an Avro file using snappy compression. All I need to do is to set a conf on Spark SQL. This time I need to use Avro. Okay, I'm sorry. I think I did a mistake over here. So let me just correct this. So all I'm doing is spark.sql.avro.compression.codec, and this time I'm going to use snappy as a compression mechanism. Then I'm going to use the data frame object, which is a Parquet data file, and write as Avro as Avro snappy, into that folder. Now let's try to inquire HDFS about this file using an ls command. I'm going to use -h as usual, which is human readable format, and let's see the size of the file. Okay, the size of the file is 644.9K. Now, if you remember the Avro file, which was a plain Avro file without any compression, was 1.7 meg, whereas this one is 644.9K when you translated that using Spark's APIs and libraries. Now, given that this problem is complete, which is step number 5, let's look into step number 6. Now, step number 6 is once again loading Avro snappy file, which is a compressed file again, right? So let's try to load this compressed file, and then we'll look into what kind of operation we need to do. Let me store this in a variable named Avro data, and same thing, SQL context dot read dot Avro. Paste this, and let me try to remove the space which can possibly cause an error. Now all I have to do is to convert this into a JSON format, which is a non-compressed JSON format. Now all for this too, there are ready-made methods available. I am going to take the data frame and I'm going to say to JSON dot save as text file, because JSON is a text format, so you're taking that as a text file. Whereas Avro and Parquet, they are not like plain text formats. They have some sort of a formatting internally, which is difficult for human eye to understand or read. Now let's inquire HDFS and look at the JSON file without compression, how big it is going to be. This is 6.5 meg. So far, the biggest file size that we have seen. Now let's try to look at the first few lines of this JSON file, and to ensure that it is in fact written as a JSON format. Now all I'm going to do is use the cat command and use a head as a suffix to the command so that I get only the first few lines of the file. So as you can see, every single line is JSON. It carries the schema and also the data. Next is, let's try to zip the JSON file using Gzip format. Now, this compression may lead in a lot of saving of your disk space. So let's try to do this. Just like we did for the text files, we need to supply a class which is responsible for this compression. In this case, the problem is asking you to use gzip. So let me do org.apache.hadoop.io.gzip codec and give the new file name. Uh, I think it is io.compress.gzip codec. So let me include that as well in the package name. Now let's inquire HDFS about this file. Okay, I'm going to save the paste the file name. Okay, this resulted in a 500K file. Now let's look at the same JSON file without compression, how much space it has taken on the disk. This is 6.5 M, which means significant amount of disk space savings, which we have accomplished using just by using the gzip compression. Now let's look at problem number 7. This is to load the JSON file which is compressed and translate that JSON file into a CSV file which should be compressed again. Now in order to load the JSON file, we use the data frame API again. All I need to do is store this in a variable, say SQL context.read.json, and then supply the name of the path at which this zip file is located. As you can see this is loaded as a data frame with all of the the fields coming in as JSON columns. Now let me copy this. First, I need to convert this JSON into a text format. For that, I need to map every element of this JSON or every record of this JSON into plain comma separated text variable. All I'm going to do is use the index from 0 to 3 because it has 4 columns inside the JSON file, and create a string which has a comma separated variable, right? So I'm separating each column with a comma and trying to save this as a text file. And then I need to supply a compression codec. The problem is asking you to perform this compression using gzip. So I'm going to use the same class that we have used in the past for all of the gzip compression, that is org.apache.hadoop.io.compress.gzip codec. Let's look at HDFS and look at the size of the file after this CSV has been compressed. Okay, CSV is a text file, so you should see a file in this which is less than a meg, because that is what we have seen when we did a plain text file compression in the past. So this concludes step number 7. Okay, now let's look at step number 8. This is to read a sequence file. Now reading a sequence file is little tricky. For this you need to understand the technique very clearly. In order to read any sequence file, you need to understand the class of the key and value which is inside the sequence file, for which let's try to look at where the sequence file is, and then the top few lines of the sequence file which will give us an understanding of the value and the key. Let me show you this by copying the sequence file. So all you need to do is load the sequence file just like any other file that you would do in Hadoop, but this time Spark, but this time you're going to use sequence file method instead of a text file method. Now this method takes 3 parameters, not just once. The first parameter is the path of the sequence file, and the second two is the class of text and the class of key and the class of value. So for this, let me enquire the sequence file by suffixing it with a head. Hmm. This is giving me the entire sequence file. So let me try doing it slightly differently. Let me download this file into my local file system and then use the head command. Okay. Uh, I need to get rid of this somehow first. Yeah, okay. This is not working. Just give me a minute. Okay, so let me do a Hadoop fs get, and let me get this file into my local, and let's try to do head again. Okay, I'm gonna say cat head. I'm not able to recollect the name of the command to get this. Okay, let me do just head. Um, oh yeah, so let me try doing head instead on the file. Okay, now I get it. I think we are getting the entire file because sequence file is not does not have lines in it. It has its own format in it. So let me try to get the first 300 characters by using the cut command. And all you need to do is you say cut -c and 300 characters. Now, if you look at the first few lines, as I mentioned earlier, um, it clearly says both the key and the value are the text class. All I'm going to do is say class of text, comma, class of text again. So this is how you read the sequence file. The trick in reading the sequence file is understanding the file itself. So you need to open the file, the first few characters of the file, to understand the class of sequence, the class of the key and the value, and use those two classes while reading your sequence file. This gives you an RDD with a key and a value pair. Now you need to extract data from this RDD so that you can create an ORC file, because ORC file requires a schema. Now in order to create a schema, you need to extract the value of the key value pairs here. So let me do that by doing a map, and I'm going to get x dot, the second element in the tuple in this pair RDD, right? So let me do x dot underscore 2. So as you can see, now I'm able to extract the second element, which is a text element, but that is not sufficient. I need to split this into multiple columns, and each column needs to have a data type so that I can convert that into an ORC file. So let me just do a quick take 5 and print it. Okay, I'm not able to print this because I'm just trying to print a text object, which is not a serializable object. So I need to convert this text object to string. So let me enhance this further by saying dot to string on this. Okay, so this is the string, right? So but this is not sufficient for me. I need to extract this string as a bunch of values with it with their own data types. So let me try to split this. Mm, Let me try to write this in a more efficient way. Instead of just splitting this over here, let me create a variable inside this lambda function, and I will, oh, okay, let me do this again. This is frustrating sometimes when I accidentally hit the keys that I'm not supposed to, but let me try to do this again. So where d equals x dot underscore 2 dot toString dot split based on a tab character. And then I'm going to uh, extract the 4 elements I need from this array so that I can create a tuple of 4 elements. Each of these elements has their own data type. I think I missed the bracket over here. Enter. So as you can see, I have a tuple now, which is an RDD with 4 string values, which is a perfect schema. However, I'm not giving any names on this schema. In an ideal world, you'll have to create a case class and convert all of these elements into that case class objects. Right now, I'm taking the default column naming, which is underscore one, underscore two, underscore three, and then I'm just going to convert this into an ORC file. So all I need to do is translate this into a data frame and use the ORC method, dataframe.write.orc, and save this into this path. Okay, I think I need to change this question so that I can specify where the resultant data needs to be stored. So let me do this correction right now, ORC, and then go back and fix the problem as well. Okay, so fix the problem here by giving the by providing the right file destination file name. So let me inquire this folder by using the ls command. Oops, I used the get command. I think at the end of the video I really get tired, but I hope this information is very helpful to you. So let me correct this quickly. Instead of saying Hadoop fs get, I'm going to say Hadoop. Okay, so I corrected this, and so this is the ORC file, as you can see, right? So let me do this again so that it's clear without any confusion. Now let me put this in human readable format so that you can get this in kilobytes and megabytes instead of some digits. As you can see, it is 289K, which is again a very impressive compression ratio. We haven't even used any compression method over here. ORC itself has compressed your file. I hope you have enjoyed this video. This is a very, very important topic in your CCA 175 exam, as I mentioned before. Keep practicing. I wish you all the very best and continue to watch my video series and build confidence before your exam. Bye.